Okay, thanks, Teresa. Well, good afternoon. Welcome to the 77th Annual School of Earth Sciences Bownocker Distinguished Lectures. My name is Matt Saltzman, and as our school director, I will give some brief words on the Bownocker series, its long distinguished history, and then introduce our speaker, Dr. Naomi Oreskes. The Bownocker lecture series dates back to 1937 and is named after John Adams Bownocker. He was both the chair of the geology department at Ohio State and the state geologist of Ohio, taking over for Edward Orton Jr. in 1906. His geologic map of Ohio actually stood for about 86 years before revisions were underway. And so his publication on building stones of Ohio also remains a vital resource to this day. To put his era in context, it was 1915 when Wegener proposed the idea of the supercontinent Pangaea. And thankfully for us, he established the Bownocker Endowment in his last will and testament, which we use to support the speaker series. The 77 names shown here read like a who's who list and subjects that range from the theory of evolution to the theory of plate tectonics, from planetary science to climate science. And because today we're hearing about the history of plate tectonics, I want to highlight a few names here in red. In 1939, Reginald Daly, who was an early proponent of continental drift when very few were, also did some influential work on the submarine gravity flows. Skipping ahead to 1964, we brought in J. Tuzo Wilson. He was a famous skeptic of plate tectonics who became one of the most influential supporters. The Wilson cycle was named after him. 1975 and 1976 must have been an interesting time. We had John Rogers and John Dewey in back-to-back years. Rogers' painstaking mapping efforts led to the broad understanding of the Appalachian Mountain Belt, and that remains an influential work to this day. Dewey did much the same in Europe and is known for explaining why the continents are so old and the oceans are so young. Mary Lou Zoback in 2003, seismologist who pioneered studies of compressional forces driving plate motion. Louise Kellogg in 2013 contributed to the study of mantle flow and its role in plate tectonics. And then in 2016, we had Lucy Jones, earthquake seismologist and science communicator. Just to list a few other prominent Bownocker speakers as well, we had Harold Urey in 1950, Nobel Prize winner, discoverer of deuterium. Ursula Marvin, shown here in her cold weather gear, first woman American researcher in Antarctica, hunting for meteorites. A list of climate change scientists and communicators, beginning with Cesar Emiliani, 1968, Wally Broker, Lonnie Thompson, Al Gore, James Hansen, and Kevin Trenberth. Quite the list there as well. Susan Solomon in 2014, also pictured here, led an Antarctic expedition, led to the theory of the ozone hole. Kathy Sullivan, geologist, astronaut, first American woman to walk on space, and Worthington resident. And then last year, we had John Grotzinger, lead scientist for the Mars Curiosity rover mission. And today, we add Naomi Oreskes to this distinguished list. Naomi is the Henry Charles Lee Professor of History of Science and affiliated professor of Earth and Planetary Science at Harvard. She got her Bachelor's of Science in 1981 at the Royal School of Mines, Imperial College of London. Spent 3 years working in the Australian outback as a mining geologist, and then decided to go back to school at Stanford, where she completed her PhD in 1990. She's the co-author of a highly influential book, Merchants of Doubt, How a Handful of Scientists Obscured the Truth on Issues from Tobacco Smoke to Global Warming, with Eric Conway. This was turned into a film, translated into many languages. The new edition this year has a foreword by Al Gore and it's been cited over 4,300 times. Naomi is co-author of, in total, 7 books and 150 articles, as well as essays and opinion pieces, some of which have appeared in the New York Times, the Washington Post, Los Angeles Times, and others. Her 2004 science article, The Scientific Consensus of Climate Change, is also very influential, cited 2,400 times. She is a Precambrian geologist by training and has written on the origins of rare earth element enriched hematite breccias in South Australia. Went on to write a book on the rejection of continental drift theory and method in American science. She's an elected member of the American Academy of Arts and Sciences, American Philosophical Society, and was recently named a Guggenheim Fellow in 2018. And now, to add to this list, she is the 77th in a long list of distinguished scholars to deliver the Bownocker Lecture at Ohio State. Thank you so much for joining us, Naomi. Hand it over to you.
Thank you. Well, thanks for that generous introduction. And it is, as I said last night, really a huge honor to be delivering this lecture. I'm going to blather for a minute while I work on sharing my screen here. I do want to make one correction. Since I'm an academic, I have to always, make a correction. In your list of distinguished previous Bownocker lecturers, you didn't mention Chester Longwell, 1947, but actually he was an advocate of plate tectonics or continental drift also, and I'll actually mention him in the talk today. So, and a couple of, more than one of the people you mentioned show up today. And I hope in the future you can mention me in the distinguished list of people who've worked on both plate tectonics and climate change. So let's get started. So my talk today is excerpted from my new book, which will be coming out early in 2021, called Science on a Mission: How Military Funding Shaped What We Do and Don't Know About the Oceans. And this is a pretty technical talk. I'm a little scared that I see 184 people on board. I am going to assume a fair amount of knowledge of geology. I hope that won't be a problem for anyone here. But the big picture questions are relevant to all sciences. And so even if you may not understand all the details of the geology that I mentioned, the bigger argument I think will still be, still hopefully make sense. So here's the cover of the book. As I said, it's coming out in February from the University of Chicago Press. And the work I'm going to present today is from one of the chapters in the book. This is actually the first time I've presented this material in public, so I'm kind of excited to do that. But it means that I probably have too much material. And so I will hopefully not speak too quickly, hopefully finish in 45 to 50 minutes. If necessary, I may have to skip some slides, but we'll see how it goes. So this book is a book I began quite a few years ago, actually before I got diverted by the small issue of climate change. And at the time, I was really interested in 2 big questions in the history of science. The first is what I would call the problem of patronage. What difference does it make who are the patrons of science? What difference does it make who pays for science? In my experience, most scientists think it doesn't matter at all, although we had a fun conversation about this yesterday with the Thompsons. But I think that there's a lot of evidence that does make a difference. And I think that as scientists and science administrators and science communicators, we actually have to be more sensitive to this issue than I think we have typically been in the past. And then I'm also interested in what I think is, kind of one of the central questions of science, which is the problem of progress. And I say problem, most people don't think of progress as a problem, but we all assume that science progresses, and we all think we can recognize progress when we see it. But how does it happen actually? We really have very few good accounts of what the conditions are or the factors that are responsible for great discoveries and advancements in science. The 20th century in earth science was a period of great progress. And 15 years ago, when I was trying to decide what my big book was going to be, my full professor book was going to be, I thought, well, I'm really lucky because geology and earth science is this incredibly interesting field that has had really major advancements in the 20th century, and almost nothing had been written on any of it. And so the field was super wide open. And so I started talking to people, including quite a few famous scientists. I had a really lovely lunch one time with Frank Press at Woods Hole and various other scientists, and just asking them, what did they think were the really important big advances in 20th century Earth science? And the scientists I spoke to were almost unanimous. Now, this conversation was taking place in the 1990s. It's interesting that climate change was not yet kind of present at the same level at that time. But the three things that people talked to me about the most were the Stommel-Arens model of abyssal circulation, the theory of plate tectonics, and discovery of deep sea hydrothermal vents and the biota that live there. So I thought, well, let me write a book about these three big discoveries. And this will be a book about scientific progress. And it'll be a happy book because I'll be writing about fun, good things. Well, so I started looking into it, and very quickly I realized that these three discoveries all had one very important thing in common. They all occurred during what many oceanographers referred to as the Golden Age of Oceanography, a period in the middle part of the 20th century when deep sea research was extensively funded and almost exclusively funded by the US Navy. And so that meant there was an opportunity to look closely at what the effect of Navy funding had been. In history, we don't get controlled experiments, but occasionally we can identify periods where there's a very strong controlling factor. And then that gives us the opportunity to do a rigorous study of how that factor seems to have made a difference. And that's what I've tried to do here. So the questions the book poses, and I should say it's a very long book, it's 700 pages, so I don't expect this to be a New York Times bestseller, but I do hope that scientists will be interested in it because I think there's a lot that we can learn about our work and our science from studying its history. So the book asks the question, what difference did Navy funding make? And also, related but not exactly the same, what difference did it make that it was the Navy and not some other organization? For example, the Forest Service. I mean, after all, the Department of Interior, the Department of Agriculture, the Department of Commerce, all fund science. So why did it matter? Did it matter that it was the US Navy and not some other group or organization? So this, I say, is essentially a problem of patronage. How do patrons influence the work that they're supporting? But what about the question of progress? What made these advances possible? And this leads to the second source of motivation for this project, which was as a kind of follow-up to my work on the rejection of continental drift and the development of plate tectonics. So having written my first book on the rejection of continental drift, looking specifically at the debate that had taken place in the 1920s and 30s and why American geologists had rejected the theory by and large. There were some exceptions, but by and large, American geologists rejected it, although quite a few Europeans did accept it or at least entertain it. So I wanted to understand why it had been rejected. So the obvious companion project was to write a book about why plate tectonics had been accepted. And there was a popular story that nearly all the scientists I knew who were old enough to have been part of it told about plate tectonics, and it involved the Navy. In fact, the claim was made by many senior scientists that it was Navy funding that made plate tectonics possible. That Alfred Wegener had proposed continental drift in the 1920s, but at the time, people said, we knew almost nothing about the seafloor. And this was a major obstacle, a major reason for rejecting continental drift theory, that we simply didn't know enough about the seafloor. But after World War II, US Navy funding led to critical oceanographic investigations that yielded key data about the seafloor, especially seafloor magnetic stripes. And that led to revisiting the question and the acceptance of the idea of drifting continents as part of the theory of plate tectonics. Well, as a historian who had written a book about the continental drift theory, I knew that at least one part of that popular story was definitely false. Continental drift theory was not rejected because there was insufficient evidence to support the theory. And in my first book, I go into this in excruciating detail. It's a 10-year book, so it has to have a lot of detail. But in that book, I showed that there was abundant evidence that the continents had previously been connected, the evidence of Gondwana land and Pangaea, the fossils, the stratigraphy. And there was also abundant evidence of apparent polar wandering. Paleoclimate indicators showed beyond any reasonable doubt that either the poles had moved or the continents had moved. And most people thought that it was almost certainly the latter because in the same time period, you could find glacial deposits in Australia and tropical deposits in Europe. So there was strong evidence that it wasn't just that the climate zones were changing or that the whole Earth was hotter or the whole Earth was colder, but that the continents actually might have moved. And if they had, that would explain these paleoclimate indicators that were otherwise very perplexing. And these data were broadly accepted as correct. The question was not, were the data right or wrong? The question was how best to explain them. Now, as for the oceans, it is true that there wasn't a lot of good data from the deep sea, but there was enough data to know that the seafloor was mostly basalt. Dredging from the 19th century and early 20th century oceanographic expeditions had always brought up either just muds and foraminiferal oozes, or they brought up basalt. And so existing theories that explained these changes in the continental relationships through sunken continents just would not work. Now, but that said, there was one part of the popular story that did seem plausible. So as I said, in the 1920s, there was a robust debate over the theory of continental drift, and the theory did receive some support in Europe, Australia, South Africa, and India. In fact, actually in the continents that were actually Gondwana land. So the geological evidence there in some ways was more obvious to people than it was here in North America. But in the United States, it had been mostly rejected. And it is true that it took new data to reopen the debate. And it is true that some of that data, or actually quite a bit of it, came from the seafloor. At least that's what seemed plausible. And therefore, it seemed plausible to credit, at least to some extent, the Navy. So in the rejection of continental drift, I focused on this earlier debate, why scientists had rejected continental drift despite a robust debate and a large body of robust data. But to the extent that I discussed the reopening, which I only did very briefly at the end, I had pretty much accepted this popular story, this standard view. I now view that part of the popular story as false too. So history also progresses based on evidence. And now I believe that the historical evidence actually suggests the opposite, that the overall effect of the US Navy was to delay the development of plate tectonics because of the adverse effects of secrecy. That is to say that the popular story is not only wrong, but we actually can show why it's wrong. And there's actually very rich historical data. And that's what I'm going to show you today. So the key figure in this story is someone who most of you have probably heard of, the Princeton geologist Harry Hess, who lived from 1906 to 1969. So his life is sort of right smack in the midst of this story. Now today, Hess is famous for being generally credited as the developer of the theory of seafloor spreading, which he began to articulate between 1959 and 1961. And this was critical in reopening the debate in the United States over moving continents. But the argument he made did not, in fact, rely on new data from the seafloor. In fact, his inspiration to revisit the topic came from paleomagnetic work, terrestrial paleomagnetic work that was being done in England. But what is true is that the model that he built his story on did rely on oceanographic data, did rely on deep sea data, but he had already developed it in the 1930s. And he had developed a theory about this in the 1930s. So in other words, both the data and the theory were actually already developed in the 1930s before the US Navy really became a major player in this story. But his progress had been stopped. In fact, it came to just about a complete standstill, first by World War II, and then by military classification of the relevant data. So for our purposes, the story begins in around 1932 when Hess finishes his PhD at Princeton, studying ultramafic rock. His PhD focused on the problem of layered mafic intrusions, which people were very interested at the time as a possible analog for Earth's structure. The idea had been put forward that the upper felsic layers of layered mafic intrusions were analogous to the Earth's crust, and the lower mafic and ultramafic layers were analogous to the mantle. Now, one of the things that we saw in these layered mafic intrusions was that there were big density differences between the upper portions and the lower portions, between the felsic and the mafic rocks. And that, therefore, was probably or possibly true of the crust and mantle as well. And this was related to the theory of isostasy, the idea that low density crust was floating in a higher density substrate. Isostasy was important. These density differences were very important because they were a critical point in Wegener's argument for continental drift. In Europe, most people had subscribed to this idea of sunken continents, that once the continents had all been connected, and that would explain why the fossils in stratigraphy were so similar. But as the Earth had shrunk, pieces of them had collapsed, and that had disconnected the connections that had previously been there. So Gondwana land hadn't drifted apart, but it had collapsed apart. But the isostatic argument proved that that couldn't be correct, because both petrology and the gravity data showed that the continental crust was mostly granitic and the ocean was mostly basalt. And there was no way that the light granitic rocks could sink into the dense basaltic rocks. So the theory of isostasy, which was more or less accepted around this time, simply told us that the sunken continents idea could not be correct. And this was a major part of Wegener's argument to say, so if it's not sunken continents, it has to be something else. And that something else is drifting continents. And because Hess was working on layered mafic intrusions, we know that he was very aware and very sensitive to these arguments about the crustal differences, or the petrological differences between the crust and the mantle. Now, I just want to say one more thing about isostasy, because it's really important to the whole discussion. The theory of isostasy had been broadly confirmed in the early 20th century. It actually had been confirmed in the late 19th. And one of the really important pieces of evidence was the Fennoscandian uplift. Scandinavian geologists, as early as the mid-19th century, had recognized that central Scandinavia had seen significant uplift since the last glacial maximum. So for example, they could see raised beaches that had sort of gone up and up and up. And this is actually discussed by Charles Lyell in the Principles of Geology. So actually, already by the 1830s, people were aware of this issue. In the late 19th century, the idea of isostatic rebound offered an explanation for what the geologists had seen, that the Fennoscandian shield had been depressed under the weight of glacial ice, and that it had rebounded when the ice melted. But this could only be true if the mantle were plastic, or at least behaved in an elastic manner. It had to be yielding to some extent. And so Wegener's argument that was accepted by many European scientists was that the Fennoscandian uplift proves the possibility of vertical motions through the crust, that the mantle was yielding to vertical motions, and therefore maybe it could also be yielding in the face of horizontal motions. And this is just a graph. This is from 1888, De Geer. This is his map showing the extent of uplift in the Fennoscandian region, where you can see this very extensive uplift of at least up to 10, oh, I'm sorry, I've forgotten now if it's meters or centimeters. I believe it's meters, up to 10 meters or 11 meters in the northern part of, well, sort of central Sweden and Norway. So perhaps because they were well familiar with the Fennoscandian evidence, nearly all European geologists accepted isostasy, also European geophysicists, and quite a few of them were at least open or at least receptive to the idea that this could help to explain how continental drift could happen. And one of the people who got involved in this discussion, he wasn't an advocate of drift, but he was actively involved in the conversation about it, was the Dutch geophysicist Feeling Venning Meinitz. But even for those who were sympathetic to continental drift, there were a lot of big questions. The continental crust was not uniform, so why should we assume the oceanic crust was? And even if the mantle were yielding, was it yielding enough to permit large-scale displacements of the type that Wegener was arguing for? Now, we knew what drove the Fennoscandian uplift. It was the melting of glacial ice. But what would be the force that would drive horizontal displacement? And if there were active displacements, but an idea that people had then is that if there were active displacements, then they might show up as gravity anomalies. For example, if the crust thinned around an advancing continent or thickened behind it, or was in some way deformed, that might show up as a geophysical anomaly. I think I'm going to skip this because it's not essential, and I want to make sure that we get to the key part of this talk. So some of these questions could be answered by careful gravity measurements at sea. At least that was the idea. Detailed geophysical analysis could help to at least constrain what some of the possibilities could be. And Venning Meinitz had done something really important. Gravity is hard to measure, and especially if you don't have a stable platform, but he had developed a gravimeter that could make accurate measurements at sea. And he was the first person to do this. So his work was the first time that anybody made gravity measurements in a marine environment. And in the 1920s, he had used this to great effect in a series of expeditions to the Dutch East Indies, or what we would today call Indonesia. One of the things that he had seen and documented in his work was a band, a very significant and very dramatic band of large negative gravity anomalies that sort of worked its way around Sumatra, Java, and then bent around the Celebes and Borneo. And it paralleled what we would now call the island arc. That is to say, it paralleled the arc of active volcanism and active earthquake activity in this region. So there was sort of a strip of gravity anomaly, a strip of volcanoes and associated earthquake epicenters. And this is just a little detail from the same map. Venning-Meinitz argued that these relationships were obviously not a coincidence, but that they were evidence of some kind of large-scale tectonic activity taking place, possibly related to large-scale crustal displacement, so earthquakes, volcanism, and geophysical anomalies. And he became part of a group of scientists, mostly in the Netherlands, who began a very serious scientific discussion of the possible role of mantle convection in driving tectonic activity and possibly driving continental drift. And this is just one example of a picture that was drawn at the time. This is from the Dutch geologist B.G. Escher, who, by the way, is a half-brother to the famous artist Escher. And in fact, there's a story that goes, I don't know if it's true, but that, Escher's work, the artist Escher, his work is in a way very crystallographic, right? It has all these axes of symmetry. And there are some people who think that Escher, the artist, was influenced by his brother, half-brother Escher, the geologist. In any event, Escher was very interested in this work, and he proposed this model in 1933 based on Venning-Meinitz's data. Now, I'm not going to go into the detail of this, but you can see a lot of really interesting things in this model. You can see convection currents in the mantle. You can see parts of the crust being thickened and downward slabs moving back into the mantle. You can see eclogite. He has the idea that we have the formation of eclogite, where crustal material is being subjected to higher temperatures and pressure. And you see an association of volcanism with rising limbs of convection currents. So this is 1933. And again, here's just a detail of the same thing. And notice the thickening of the crust in the areas of the downward sinking convection currents. So this work came to the attention of a group of American scientists centered around William Bowie, who lived from 1885 to 1961, and was chief of the Geodesy division of the US Coast and Geodetic Survey. The geophysicists in the audience will recognize this name because AGU has a Bowie Medal, which is one of the highest honors in the American Geophysical Union. Bowie, because he worked at the Coast Survey, had good contacts in the Navy. And he had the idea that maybe they could invite Venning-Meinitz to the United States to measure gravity at sea on a submarine the same way he had done in Indonesia. But in order to do this, they would need a young scientist to go to sea with him and help him out. And so Bowie reached out to a friend, the Princeton professor Richard Field, who was a sedimentary petrologist who had been using gravity measurements to try to better understand reef structure. They were also co-founders of the AGU. In 1938, Field would become the first president of AGU. And Field recommended this student who had just got his PhD, so the timing was perfect, and that was Harry Hess. They undertook 3 gravity surveys in the West Indies. The first in 1929, the gravity measuring cruise of the USS submarine. Actually, that was before Hess had actually quite finished his PhD. Then a second cruise on the US submarine S-48, and then a third cruise on the USS Barracuda, where another rising young geophysicist joined, and that was Maurice Ewing, who would later go on to become the head of the Lamont Geological Observatory at Columbia. The S-21 was imagined simply as a feasibility study. What Bowie and Field were hoping for was that they could simply demonstrate the feasibility of doing this work. But in fact, it returned very, very significant results. And what it showed was that the pattern in the West Indies was extremely similar to the pattern in the East Indies. In particular, there was a band of large negative gravity anomalies associated with deep parts of the ocean. I should have said, by the way, in Indonesia, the gravity anomaly is exactly coincidence with the deepest part of the ocean in that area, what we would now call, the ocean trenches. Well, actually, they already called them trenches then. So the gravity anomaly is associated with deep trenches and also parallel to bands of volcanic and earthquake activity. So Venning-Meinitz and Hess began a discussion through letters that continued after Venning-Meinitz went back to Europe. And these letters have been preserved at Princeton University. And so this work is based to a large extent on these letters, as well as a certain amount of published work, but primarily on the discussions that they had with each other. So in this correspondence, they're talking about the meaning of the negative gravity anomalies. And the idea begins to develop that you could explain this negative gravity anomaly if the low density granitic crust was thickened by some kind of tectonic disturbance or displacement. And they developed what they called the buckling hypothesis. But they realized that for the buckling to occur, there must be large-scale compressive forces, some kind of regionally extensive displacement, which would compress the crust and cause it to buckle and possibly bend downward into the mantle. And of course, this was exactly the sort of thing that Alfred Wegener was talking about when he talked about continental drift. So here's one example. In 1933, Wenning-Meinitz wrote, "A great negative protuberance is developing, which causes a great mass defect corresponding to the strong negative gravity anomalies. Knowing that the root must have a cross-section of more than 1,000 square kilometers, we may realize the magnitude of the phenomenon." So in other words, he doesn't quite yet know what he thinks it is, but he's saying whatever it is, it's big. This is not just a local thing. This is some large-scale crustal disturbance. Now, Wenning-Meinitz had called it the buckling hypothesis, but his Dutch colleague Philip Kuenen preferred the term tectogene, literally a feature caused by tectonic activity. This was a term that had originated with the German geologist Erich Harman. So the anomalies could be explained by some kind of downfold or downward compression of the crust. And the downward compression of the crust could be explained by some sort of regional compression. But what caused the regional compression? And the obvious answer was continental drift. And so Hess, makes this very simple sketch to explain what he thinks he's seeing in the Caribbean. So you can see on this sketch that on the right-hand side is the gravity anomaly with the earthquake epicenters also noted. And he just has this kind of schematic, the idea that this thing in the middle, the Caribbean Sea, that there's some kind of crustal block that is moving to the east. And so he calls it the Caribbean block, and he says the Caribbean block is being displaced, and that displacement is what explains this zone of compression and tectonic activity, volcanism, and earthquakes. Now, this is though all happening at the exact same time that a group of American geologists are trying to explain away continental drift. So as I've said, most Americans didn't accept the theory, and there's a long, complicated story why that is. And if you're interested, then you can read my first book. But just at the very same time that Hess is analyzing this data and having this rich conversation with Wenning-Meinitz, two very famous, very prominent American geologists, Charles Shuker at Yale and Bailey Willis at Stanford, had come up with an alternative explanation of the paleontological evidence of drift. They argued that the fossil homologies, the fossil evidence, the fossil similarities between Africa and parts of Europe or Africa and South America could simply be explained by what they called isthmian links. That is to say, land bridges, what we now would call land bridges, narrow strips of land that had perhaps been exposed during sea level low periods at various times in Earth history. And therefore, they argued, there was no need for the theory of continental drift. Now, this theory was problematic in 100 different ways, and if we had more time, we could talk about it. But for the purposes of my argument today, it's sufficient to know. So here it is, 1932, a young Harry Hess, he's just got his PhD, and he's got this really, really exciting data that he thinks proves there's some kind of big crustal displacements taking place. And at the very same time, two of the most famous, prominent geologists in America, Shuker had been a president of GSA and a vice president of AAAS, they say, oh, you don't need that theory. Here's how we explain the fossils. So you can see that Hess is in a very delicate position. And so he proceeds cautiously. And you see this in his writing. It's tentative. He's not sure, or maybe he is sure, but he doesn't want to overstate the case. So he writes, the negative gravity strip has important geological implications. It supplies definite indications of a major orogenic belt and intimates the way in which the Earth's crust yields to orogenic forces. So you see this language of implications, indications, and intimations. This is very tentative language, and it may give the impression that he's very unsure. And by the way, I should say this comes from a published article. So when he's writing to vending mines in private, he's pretty confident that they're onto something big, both literally and figuratively. But when he speaks in public, he's much more careful. So remember, he's only 27 years old, and he's going up against some of the most famous people in American geology. But despite that, he still continues, and he still pushes the argument. And he compares what they found with the previous work in the East Indies. And he says, this strip of negative gravity anomalies in Indonesia was continuous for the length surveyed, 5,000 miles. In other words, it didn't end. They stopped the survey because they ran out of time and space, but the thing did not end. And so Hess says, this implies the deformation of the Earth's crust is taking place in a single and continuous narrow belt. So you see, he has this idea that these belts are actually continuous. The terminations of the negative strip were not reached in the regions surveyed. Do these strips gradually die out laterally? Do they terminate against fault or shear zones? Or are they perhaps continuous around the world? So you can see here that he is speculating about what we would later call plate boundaries. And as I've just said, in their private correspondence, it's clear that both Vending Meinitz and Hess are sure that they are onto something big. Vending Meinitz writes in a letter in 1933, the gravity profile west of Sumatra may be explained by the fact that the direction of stress exerted by Asia is here nearly parallel to the gravity strip, which causes Sumatra to override the ocean floor a bit, pressing it down. Okay, so here you basically have the idea of either a continent or a continent-ocean collision with Sumatra overriding the ocean floor and the ocean floor being pressed down into the mantle. Now, the scientists had also measured positive anomalies over most of the Gulf of Mexico. And so one of their questions was, well, what caused that? And they speculated that if there was regional crustal compression, then it could increase the density of the compressed rocks. But what would cause the great lateral compression? And here Vending Meinitz wrote that he was, quote, tempted to look for the cause, or at least one of the causes, in the relative movements in convection currents in the substrata. So this is 1933, and this is the argument that his colleague Escher has put forward, that mantle convection could be the explanation for these large-scale crustal movements. And so for the next several years in the mid and late 1930s, Hess and Vending Meinitz had a sustained conversation about whether mantle convection, sorry, not convention, convection, could drive crustal motion, and whether that could explain both the large-scale regional geophysical anomalies and the associated earthquakes and volcanism. And they also considered the reverse. As the crust was folded down into the mantle, maybe it was the sinking of the crust that was triggering convection. And this was the thing then, of course, that tied their work directly to continental drift, because the idea of convection had already been proposed and discussed as the driving force of continental drift. So in the 1960s, scientists would, in fact, accept mantle convection as the driving force of continental drift. But that idea had already been proposed at the time of the continental drift debate. So this illustration is from an article by Arthur Holmes in 1929. And you can see in this article, he's showing the idea that rising mantle convection currents are responsible for the rifting of continents. The continent rifts into two pieces, which then move laterally to the right and the left. And then the convection currents sink back into the mantle. Now, there's a few things about this that obviously are different from what we would later come to think was true. So in this case, he thinks that when the continents rift, so a place like Iceland, for example, he thinks it's just a piece of continental crust that's left behind. I mean, now we would say that it's actually a piece of ocean floor. And he doesn't have in this picture, he has the downgoing convection currents. He doesn't have the crust sinking back into the mantle, but we will get to that in a moment. And I should just say, Arthur Holmes was a very, very famous scientist. And this paper we know was widely read by American geologists. In fact, not only was it widely read, but some of them thought that it had solved the problem. And one of them was Chester Longwell, your Bownocker lecturer from 1947. In 1926, in fact, even before Holmes had published the paper, he had corresponded with Holmes, and Holmes had given some talks that Longwell was aware of. Hold on, my dog is barking and I feel like it's a bit disturbing. So I'm just going to take 30 seconds to send my dog out of the room. The risks of working at home, but this was a good slide for you to have a minute to look at. So in 1926, Longwell wrote to Schuchert about Holmes's work, and he believed that Holmes had actually solved the problem of what force could drive continental motion. And he wrote to Schuchert, Holmes has a beautiful theory, and I believe it will be epoch making. So at least some scientists did think that the idea that convection currents were the solution to this problem. Some people were having that conversation as early as 1926. So now, in the early 1930s, Wenning-Meyers and Hess have geophysical evidence consistent with that idea of convection currents. Wenning-Meyers writes to Hess in 1935, I cannot see another reasonable explanation than by admitting convection currents in the substratum below the crust, rising below the continents, and sinking below the oceans, as, for example, Arthur Holmes assumes. So here we see that these scientists are well aware of each other's work. Chester Longwell is talking to Schuchert about Holmes, Wenning-Meyers is talking to Hess about it. And this idea that the rising convection currents are the driving force is being discussed by the key scientists who are involved in this debate. Now, in 1932, Wenning-Meyers had already published these results with two Dutch colleagues, J.H.F.S. Umbrove and Philip Kuenen, who had worked with him on the Dutch gravity expeditions. In Wenning-Meyers' writings, you see him being a little cautious about the whole idea. He thinks there are convection currents. He's not sure if they would cause continental drift, but Umbrove and Kuenen are sure. They are geologists and they make the link explicit. So Umbrove in 1932 had suggested that the negative anomalies represented underthrusting of low density continental crust, and that this could be caused by, quote, a northwestern movement of the Australian continent relative to Indonesia, as was supposed by Wegener. Indeed, Umbrove noted that Wegener's theory had, quote, been acclaimed by numerous explorers of the East Indian archipelago, precisely because it could explain so much of what they had observed there. But with all these theories, there was always the question, it was one thing to have an idea for how something could occur, but could you prove that it was really happening? Could you prove the crustal thickening and underthrusting really existing? And more to the point, did convection currents exist? And if they did, could they cause these features? And this question was taken up experimentally by Phil Kuenen. I can see that I'm not going nearly as fast as I need to get through all this material. So I'm going to just go very quickly through Kuenen's experiments. Kuenen does a set of bench scale experiments to show that at least in principle, if you compress crustal material from the side, you could get downfolds of the type that would be proposed by this buckling hypothesis. So in 1937-38, Hess puts these pieces together. In 1937, he returns to the Caribbean with Maurice Ewing and collected data at 51 additional stations at sea and presented the results at the 1938 meeting of the American Philosophical Society. Ewing just presented the data without significant interpretation. He simply noted the parallel with the East Indies. But Hess, however, announced what he thought was a breakthrough based on unifying the East and West Indian results. He wrote, Meyers' discovery of huge negative anomalies in the vicinity of island arcs is probably the most important contribution to knowledge of the nature of mountain building made in this century. When the significance of the huge anomalies and the structures they indicate become appreciated, a radical change in some of our ideas on mechanics and processes of mountain building becomes necessary. There can be no doubt that the major portion of the anomalies present in the negative gravity strip is due to the abnormal mass distribution in the Earth's crust below the strip. Meyers' explanation is that the Earth's crust buckles downward in a huge vertical isoclinal fold, and thus the light material of the upper crust might extend downward to a depth of 40 to 60 kilometers. And he stressed that this was a unifying theory that could explain many previously perplexing observations. And he concluded, therefore, that he is completely convinced of the soundness of the theory. And here's the picture that he then draws. So this is from 1938, presented to the American Philosophical Society. And so you can see he has it, as he says, as an isoclinic fold. So obviously that's not exactly the same as the way we imagine subduction today, but the basic idea of a large piece of the crust sinking into the mantle, creating a sedimentary basin above where sediments would accumulate, and being associated with a negative gravity anomaly, that picture is there. And moreover, he doesn't just think this is unique to Indonesia. He says, apparently all mountain systems have a tectonic history similar structurally to the present island arcs. So again, there's still more questions though. Was a down buckle mechanically possible? Cunan's experiments suggested that it was. But how were the compressive forces created and sustained? Cunan had used a plunger, and that was hardly realistic. But there's one more piece of this puzzle then that will bring us up to where these scientists got to in 1938-39, and that's the work of David Griggs. Griggs went on to become one of the founders of the RAND Corporation. He didn't stay in geology, and so his work is not very well known to most geologists. But at the time, he was a rising star. He was a newly appointed professor an assistant professor at UCLA. He'd been a member of the Society of Fellows at Harvard, and he'd done important experimental work at Harvard with Percy Bridgman and Reginald Daly. I said I would mention Daly, on the behavior of rocks at high temperature and pressure. And he decided to try to build a mechanical model that would accurately reproduce the spatial and temporal relationships. So I don't have time to go into the details here, but Griggs was very, very mathematically astute, and he was inspired by the work of M. King Hubbard to build a model that was proportional, that was truly proportional. And the main argument he made, and if I had more time, I'd go into the mathematics, because there's a very beautifully mathematically worked out argument here about if you downscale a model in size, but you also downscale it in time. So now you have a model that has to do in a few minutes or a few hours what happens to the Earth in millions of years. You have to scale the property of the models accordingly. And what he proves, what he demonstrates scientifically or mathematically, is that all existing models that people had built, and there are others that I haven't had time to talk about, were all using materials that were much too rigid. That in fact, a scale model of the mantle, to be realistic, would have to use a viscosity of 1.3 to 10 to the minus 19th. In other words, it had to be liquid. So even if you didn't think the mantle was actually liquid, the model of it, the desk scale model, would have to be. And so he built that model. And this is the picture that he drew. So the mantle is glycerin. The crust is made of oil and sawdust, so simple, easily available materials. And then he uses drums, either stationary or rotating, to simulate the effect of convection currents. And this is the picture he develops. And indeed, he finds that if he keeps one drum stationary and rotates the other, the crust thickens. First, it pulls down. You get the equivalent of a marine trench. And then the continental crust thickens. And you also get a set of thrust faults forming on the leading edge of the downward going oceanic crust. I'm going to skip this in the interest of time. And based on that scale model, he then builds a conceptual model. And this is the conceptual model, that subduction currents lead to a kind of pulling down of the crust above. This leads to an ocean basin. The basin will begin to fill with sediments. And over time, you'll get a series of thrust faults. You'll also have melting at the base of the thickened crust, which then can explain why you would see volcanism and earthquakes in island arc environments. Griggs presents this meeting at the 1938 meeting of GSA, and Hess is the chair of the session. Now, it turns out Griggs made a movie. I think it's so cool that the UCLA professor decided to make a film. Sadly, the film appears to be lost to history, so we can't see the film because that would be awfully fun. But we can see the model, the descriptive model that he makes of it. Again, I probably will skip this detail now in the interest of time. Now, there's one piece some of you may be thinking, okay, well, that's all very well and good, but it's not really subduction, because he has the continental crust thickening. He doesn't actually have the crust sinking into the mantle, as we would now today say it does. But in fact, that piece was available too. Griggs didn't actually think that the crust would rupture, but his former colleague at Harvard, Reginald Daly, did. And this was a version of the picture that Daly had developed that he had published in 1926 in a book called Our Mobile Earth. And here you can see that in this model, the crust actually ruptures and part of the continental crust or the oceanic crust, depending, actually sinks back down into the mantle. So if you put these two pieces together, it's pretty close to what we would say island arcs look like, or at least people, I shouldn't say today, pretty close to what people in 1968 thought island arcs would look like. So after the 1938 meeting, Hess summarized. He wrote, recently an important new concept concerning the origins of the negative strip in the island arcs has been reported by David Griggs. It is based on model experiments. By means of horizontal rotating cylinders, convection currents were set up in a fluid layer beneath the crust and a convection cell was formed. A down buckle in the crust, similar to that produced in Cunan's experiments, was developed where two opposing currents meet and plunge downward. If the buckle were formed entirely by tangential compression in the upper crust, it would be so weak and unstable that it could only last for a very short period of time. But by means of convection currents, the difficulty of maintaining the down buckle can be removed. And then Griggs publishes these results in 1939 in the American Journal of Science. Now, admittedly, this was not plate tectonics exactly as it developed in 1968, but we can see that it's awfully close and that all of the major pieces are there. It's a global theory. It involves large-scale continental displacements as per Wegener, but it subsumes it into a bigger theory that involves mantle convection. It's quantitatively defensible. It explains the association of gravity anomalies, volcanisms, and deep earthquakes. It's consistent with the geological evidence that had already been offered by supporters of continental drift. And Hess is theorizing that the island arcs where these relationships have now been documented are linked globally to other zones of tectonic activity. I'm going to just skip this as well because we've already pretty much talked about that. So we have all these pieces. So what happened? I mean, we can see that these guys, and I don't have time to talk about this, but this is a picture that another geologist presents of the Atlantic, pointing out that the Atlantic has its own zone of earthquakes and volcanism that runs down the mid-Atlantic ridge. So what happened? Why did progress stop? Why didn't they just keep working on this and figure out the rest of the story? Well, the short answer is war. On the S-21, Hess had found it difficult as a civilian to get help from the sailors, and so the Navy had made him a lieutenant in the Naval Reserve. When war broke out, Hess was called up, and in 1941, he went to sea. He worked on bathymetric mapping, which the Navy was interested in for navigational purposes. And this is a very cool map that Hess made while he was in the Navy that was only declassified many years later. But you can see the circum-Pacific trenches all along the northern and western side of the North Pacific. He also discovered geos, the flat-top mountains that he interpreted as drowned volcanoes. But none of this could be published during the war. Now, that's not particularly surprising. It's not very shocking that war interrupted scientific work, but we might have thought that after the war, Hess would have returned to this work. I mean, he's so excited about it. He thinks he's on the verge of a major breakthrough. He's gushing about it to colleagues and friends and presenting it at GSA, and Griggs is publishing in the American Journal of Science. So you might have thought that these men would have been very eager to get back to work and continue on what they thought was going to be a major scientific breakthrough. And especially now, because now Hess has a lot more relevant data from the deep sea. But after the war, none of these data could be discussed. None of them could be published. They couldn't even be discussed because of secrecy, because essentially all the bathymetric data, with only a very few exceptions, were classified. And not only could Hess not publish on these data, he could not even discuss them with colleagues unless they had clearances. So he couldn't discuss with Venning-Myers what he was now learning about the deep sea. And we know this troubled Hess because he spent the rest of his life trying to get these data declassified. So I know I'm like almost up to the hour here, so I'll do my best to try to finish this story. And Matthew, can I go over a few minutes? Would that cause a big crisis in the schedule?
Yeah, no problem. You can.
All right, I'll keep going. If anyone needs to leave, I won't be offended. I won't even see you leaving. So, okay. So Harry Hess spends the rest of his scientific life trying to get the data declassified. Now, I don't have time to go into all the details and all the historical documentation. There are a lot of letters and a lot of memos. It's actually very, very well documented. The details are in the book, and I hope that if you're interested, you will be motivated to read it. But what we know, based on the documentary evidence, is that Hess reached out repeatedly to Navy officers, to other prominent scientists who he thought could have influence with the Navy, to try to persuade the Navy to release the bathymetric data for its scientific significance. So here's just one specific example. I'll just skip the example and hope that you believe me, but it's in the book. So we know that and the Navy refused. The Navy said no. The Navy said these data are too important for national security. So then Hess argues back that, yes, we understand that national security is important. We care about national security, but we also care about the progress of science. And the progress of science is important for the Navy too, because science helps the Navy. And so therefore he says, it's in the interest of the Navy to declassify at least some of these data, maybe from the less sensitive areas, in order not to impede the progress of science. The Navy responds to this question and says, okay, prove it. Give us concrete examples of cases where progress is being stymied by secrecy. So Hess himself makes the claim that scientific progress is being blocked. And the Navy says, well, give us some examples. And several oceanographers did. And they included Roger Revelle at Scripps and Joe Warzel at Lamont. So these are two scientists who work really closely with the Navy, who like the Navy, who have many good friends in the Navy. Roger Revelle himself is a Naval Reserve officer, but they write back long and rather passionate memos. One of the key problems, they say, is that they're unable to discuss their results with their European colleagues because the European colleagues could not be given clearance. And so this obviously would include people like Venning Mines and Umbrove and Cunin and the others. But another problem, and a very interesting one, given that we're here in a geology department, is that they couldn't discuss the results with their colleagues in geology. And Warzel particularly goes into great detail about how he wants to discuss this with his colleagues in the geology department, and he can't. And he says the problem is that to interpret bathymetric data, you need geological insight because you need to know something about what these structures are likely to be. But almost no geologists have security clearance because they're not judged to have a need to know. And so he can't discuss the results with his geological colleagues. And this, he feels, is actually blocking him from understanding the data that he has. Revelle agrees, and he says this is an especially important problem for bathymetric data because bathymetric data are always incomplete. And he writes, it is necessary to collate and extrapolate incomplete sounding data using geologic knowledge of the principles underlying the contouring of deep sea topography. These principles are very inadequately known at the present time and will be best developed if a widespread interest in the topography of the seafloor can be stimulated among competent geologists. But it was impossible to do that, impossible to stimulate that interest because geologists were denied access to data, and even people who had access were denied permission to publish. At Lamont, Warzel complained that even people who did have access to data were repeatedly refused permission to publish, so increasingly no one wanted to work on bathymetry. He wrote, we now find it virtually impossible to get any of the young scientists to work on topographic problems. So Warzel argued that classification didn't just demoralize individuals, it discouraged entire lines of inquiry. And again, this is another example. I can skip the details, but Warzel writes to Revelle in 1952 saying how people have abandoned work. They've actually stopped working on certain things because they're afraid that even if they do the work, they won't be able to get clearance to publish it. So the idea that deep sea data collected under Navy auspices push science forward is actually at odds with which these scientists themselves experienced. What they experienced was annoyance and frustration, and they felt that progress was being blocked. And despite their repeated entreaties, including from people as famous and prominent and respected as Roger Revelle, the Navy refused to declassify the bathymetric data. In fact, we can argue that it's the same confluence of interest that makes the Navy interested in funding marine geophysical work is what leads it to keep it secret. In other words, the Navy thinks this does matter, that these are important data, and that's why they won't let them be public. At one point, Revell is so frustrated that he reaches out to Emmanuel Piori, the chief scientist of ONR. Maurice Ewing reaches out to Piori, and Piori writes back to Ewing, and he claims that in general, the military does support publication, but, he says, in some areas of some fields, it is occasionally necessary to request that a paper be withheld from publication because of military interest, which may be revealed. We have faced this problem of classification of research results in many different fields, and usually have been successful in finding the means to protect the scientific priority of the investigator in publication of his results, while at the same time protecting the interests of national security. Often this has been a difficult task, and we have been a particularly difficult time in the matter of a classification guide in the field of oceanography and geophysical investigations of the ocean and ocean bottom, which are so closely allied to many problems of great importance in Navy operations and strategy. And indeed, in fact, they never developed that guide. They never came up with a system of figuring out what could be published and what could not. Now, historical documents suggest that the military thought that the scientists were just whining. After all, scientists were quite happy to take Navy money, and if we're all that bad, then why didn't they just go somewhere else? Well, of course, the reality was that there was nowhere else to go. In oceanography and marine geophysics and geology, there was no other funder for this kind of work. In fact, some scientists did try to go to NSF, and in general, NSF refused to fund projects in these areas on the grounds that the scientists could go to the Navy. So the fact is that Harry Hess was stuck. And how do we know that? How can I say that? Because for 20 years, from 1939 to 1959, he made no progress in the issues that had engaged him so well in the 1930s. The issue that he thought he was on the verge of a major breakthrough, he now does nothing with. And it's not until 1960 that he begins to work on the issue again. And it's based on an invitation from Maurice Hill, the British oceanographer in geophysics, who's writing a big compendium called The Sea. Hill wanted Hess and Fisher to write the chapter on trenches, and they did. Here's the picture that they published in 1963. It's definitely got more detail than what we saw in 1938. He's added a lot of information about what he thinks the rock types are. He's added the seismic velocities, and he's added the density of the rocks that would correlate with those seismic velocities. But the basic picture of a vertical downfold is the same. It hasn't changed at all. He's made no progress. So despite all the extra data that he has access to, the picture of a crustal slab moving down is essentially the same as what it had been in 1938. Sorry, there's something wrong with the slide, it's a bit cut off, but it's at the same time that Hess then writes the paper for which he would become most famous, the paper on the history of ocean basins, in which he proposes the theory of seafloor spreading. But if we ask the question, well, what inspires him to write this paper? What new data is in it? Well, actually what we see is there's no new data. The only seafloor data that he invokes is the data from the geos that he had collected during World War II. And there's no new data because even in 1963, he is still not permitted to publish the data from the seafloor, and he's not permitted to talk about it. And if we actually read this paper and ask, well, what inspired him to reopen the debate, right? Because if you'll recall, at the beginning of this talk, I said that the popular story was that the new data from the seafloor helped to reopen the debate, and that was the critical thing. But actually, if you read what Hess says himself about why he is now revisiting this question, it's not the seafloor data. It's the terrestrial paleomagnetic data presented by Keith Runghorn and Ted Irving and others in the United Kingdom. It's the terrestrial paleomagnetic data that shows that the apparent polar wandering paths are caused not by the poles wandering, but by the continents wandering. So to sum up, and I apologize for going a bit over, in 1952, Roger Revell wrote a memo to the US Navy in which he argued that because of secrecy, because of data classification and the inability of scientists not just to publish their work, but even to talk about it, he said it could, quote, take 25 years to do what otherwise might have been done in 5. Well, everyone who knew Roger Revell said he was the perennial optimist, And history suggests that he was being too optimistic here as well. Because Hess and his colleagues were on the verge of a breakthrough in global tectonic theory in 1938. They thought they were on the verge of a breakthrough. And as a historian who studied it, I think they were on the verge of a breakthrough too. They got there 30 years later in 1968. But for Hess, it was too late. He died in 1965, and he never got over thinking of that downward crustal slab as vertical. Thank you very much.
Okay, at this time, we're going to open up the floor for Q&A. So please, those in the audience, post your questions in the Q&A box down at the beginning or at the bottom. I want to, so Naomi, that was excellent. And I feel especially moved because island arcs and orogenic belts are fundamental to the work that I do.
Oh, cool.
So that really gave an important context to this idea that geoscientists like me have the privilege of just accepting as fact. I want to take advantage of my position as the facilitator to ask the first question while people are still formulating there. So I imagine you're familiar with this book, Naomi, The Structure of Scientific Revolutions. It's by Thomas Kuhn. It's one of the seminal publication sort of related to this, but one of the central themes of this book is the differences between normal science and then periods of that are disrupted by paradigm shifts. And so what I'm wondering is, because pretty much all the research that you discussed here was done right on the verge of a paradigm shift. And so what role does that play in the relationship between, or the effect of patronage on science, being on the verge of a paradigm shift versus being in a period of normal science?
Well, that's a tricky question because Kuhn's theory is obviously a complicated one. And yes, I know that book. I think I have about 7 copies of it. I've taught it probably most years of my teaching for the last 25 years. So I think that Kuhn's great contribution to the history of science is his focus on the community structure of science and the role of consensus. And I'm deeply influenced by that aspect of his work. I think he's wrong about the sharp dichotomy that he sees between normal and revolutionary science. And I think this story proves that, because you see that, so people always talk about plate tectonics as being a revolution, but if we take seriously the work that was being done in the 1920s and 30s, then we have to say this revolution took 40 years. And that's not really what Kuhn had in mind, right? Especially when he talks about it as a Gestalt shift. I mean, this is not a Gestalt shift. This is people putting together the pieces of a puzzle. So in that sense, it's normal science, right? I've got this piece, I've got the West Indies, I've got the East Indies, I've got the Kunin's experiments, I've got Griggs experiments, I've got all these pieces, and it's starting to put together into a coherent picture. And that all takes time, and it doesn't happen overnight, and it's not a Gestalt shift. So I think that the story of the Continental Drift is a really good one for seeing some elements of Kuhn's theory that are very powerful and useful, and others that not so much. And I do actually talk about this in the Continental Drift book. The other thing I would say about it is just that it also points out something that I think is wrong in Kuhn's work, which is he says that you can't be a mature science if you don't have a paradigm. And he talks about science being pre-paradigmatic. And he actually uses geology as an example. He says, well, Lyell's principle of geology was an exemplar, and it's the paradigm for geology. And so therefore geology is not pre-paradigmatic, geology is normal science. But the reality is actually Lyell's work was exemplary for some people. It was exemplary for stratigraphers, but it wasn't really that important, say, for people who are worried about tectonic issues. And in tectonics, there was no reigning paradigm. And the whole first third of my Continental Drift book is actually about this. So there's a lot of different competing theories. Europeans mostly believe in sunken continents. Americans mostly believe in geosynclines, but there's other hypotheses out there too. And one of my favorite documents that I ever found anywhere was Bill Menard's class notes from when he took tectonics when he was an undergraduate. And this is in the book, you can look it up if you're interested, but the professor is laying out all the different theories of mountain building. And he's got a list of 15 different theories of mountain building. So there is no one paradigm. And yet geology at this time is clearly a science. So I think Kuhn has overstated the ubiquity of unifying paradigms. Yes, we definitely have them at times. And yes, they're important when we do have them. But there are also times when scientists are grappling with things that are just frankly confusing and there isn't agreement on the issue.
That's a great answer. And it sounds like I just need to read your book.
Well, you know, it's hard for me not to just keep saying that over and over again. But when you've been working on something for 30 years, you know, it used to be I'd say, well, I'm trying to finish a book on this. Now I can say, well, actually, I do have a book where I talk about this.
I've got another one here from the audience. So someone says, this reminds me a lot of the way the military is studying climate change as a national security threat. What is the current role of the DoD, Department of Defense, in climate change research? What areas do they research/support research in, and why?
Oh, that's a very interesting question. And that does raise an important concern, right? That if a lot of the work that was being done was done by the military, actually a couple of us talked about this yesterday in terms of the Byrd Polar Center work. I mean, the DOE does support polar work and has for a long time. So there could be a concern that if too much of the work was supported by DOE, that there could be a concern that it wasn't being adequately made public. I don't know what the agreements are. I mean, maybe some of the Byrd people can talk about that, what their agreements are. I think in general nowadays, you know, back in 1945, 48, scientists were just starting to figure out what their relationships with the military would be. And I think we have better agreements now for publication of work. I think there's better understandings in many areas for the importance and necessity of making work public, but there's still a lot that remains classified. I would say the main reason why I wouldn't be too worried about climate science is that although it is true that the military funds polar work, most of the major work on climate has been funded mostly by NOAA and NASA, to some extent, a lot of paleoclimate work by the National Science Foundation. There's a greater diversity of funding sources in climate science. And that's one of the arguments of the book, one of the overall arguments. It's not that the Navy was a bad patron of science. I don't think that's true. I think in quite a few important ways, the Navy was a good patron, but it was problematic that so many eggs, so many scientific eggs were in one basket. And so I think one of the take homes from my book is the importance of diversity of funding, diversity of patronage in scientific work.
So we have one more time for one more question. So this one comes from actually Professor Mike Durand in Earth Sciences. So he says, how did we end up with the narrative that the Navy measurements were so transformative?
Yeah, that's a great question. Well, the ways in which myths become created and sustained is a really, really complicated question and probably beyond my expertise as a historian of science and scientist. But I think that part of the answer is that scientists in the 1930s were embarrassed. I mean, I don't think most of them admitted it in public. A few did, but most didn't. But, you know, here it is, you have this incredibly important theory developing, right? And Tuzo Wilson, I think, is someone who actually was embarrassed about it, but he's rare. You have this great theory being developed. And it turns out actually a lot of the scientists in the 1960s, particularly the geophysicists, particularly people at Lamont, didn't actually even know about Alfred Wegener because they had come into geology or earth science or geophysics often from physics. I once had a very nice conversation with Walter Pittman at Columbia, and he said, yeah, he came into marine geophysics from engineering. He said he didn't know a thing about geology. He didn't know the difference between, he wouldn't have known the difference between a metamorphic and a sedimentary rock if it hit him in the head. So these people knew nothing about the history of geology. They knew nothing about this earlier debate. They didn't even know who Alfred Wegener was. Bruce Hazen once wrote a memo in which he referred to Alfred Wagner. Now, I think that Hazen was dyslexic, so it's possible it was just a spelling error, but there's a point at which Hazen actually writes to a secondhand book dealer in London to try to get a copy of Wegener's book, because he's never read it. So most of these people knew nothing about this, and to a certain extent, they reinvent the wheel. And a few people say, well, wait a second, this guy, Alfred Wegener, had this idea back in the 1920s, you know, how come you're not crediting him? And so I think that part of what happened was that scientists kind of scrambled for a story. They scrambled for some account that made sense, so it didn't look like they were just being irrational or that they'd made a giant mistake in the past. So I think two things happened. One thing is that they created this whole story about how there wasn't enough evidence, but now that we had all this great work from the ocean, now we do have enough evidence. And it wasn't totally wrong. Like a lot of myths, I would say probably all myths work because they're partly true. So there is a lot of data from the oceans that begins to come out, but it's not the bathymetric data, it's the paleomag data. And the paleomag data is very important, but even there, the most important data doesn't come from the US military, it actually comes from the Admiralty. And in the book, I talk about that. But it seemed plausible, right? It seemed plausible to say, well, we didn't have enough data then, but now we do, so it's okay. And we didn't screw up, you know, it's an understandable thing. I mean, the other popular story they told, which was completely false, was the mechanism argument, that a lot of scientists, and some even published this, Stephen Jay Gould published this, said that the reason that drift had been rejected in the 20s was because there was no mechanism. And when I started doing research, one day in the library, one day proved to me that that argument was false. And I'll never forget this. This is a great story if any graduate students in the audience. I was very upset because Stephen Jay Gould, my hero, had written something that was untrue. And I went to the professor I was working with, who ultimately became my thesis advisor, although at the time I was just taking a seminar with him. I thought this was just a seminar paper. And I went to him and I'm holding Gould's book and I say, Peter, Stephen Jay Gould has this all wrong. And I'm like really upset. Peter looks me in the eye and he goes, fantastic. Right? The world's your oyster. Go prove Gould wrong, which I did. So yeah, there you go.
Naomi, thanks again for being here. And
You're welcome.
I'm going to pass the mic back to Matt Saltzman.
Yeah, thank you so much, Naomi, for that really fascinating, enlightening talk. I hope you bless us to put this recording on our website because I'm going to watch it again.
Okay.
I'll read the book too, of course, but yeah, that was a great talk. And someday we hope you can visit Ohio State. It's just a beautiful fall day out here right now, and you're welcome anytime. So
Thank you.
again.
That would be fun. I'd like that. I hope someday we get to do that. And you owe me a dinner, right?
At least. Okay, thanks everybody, and thank you, Naomi, and we'll see everybody.
Okay, thank you. Bye.